Hello everyone, welcome to this short webinar. This is going to be about wind loss on SimSolid and will work as a quick overview into simulation tools for AEC application. My name is Alejandro Lopez and I'm the one who will be leading this short webinar. And let's get started. But before we continue with all of this, I want to let you know that this is going to be recorded and it will be uploaded to our YouTube channel so you can take a look into this presentation for any particular topic and for the whole presentation in case you are interested into watching it once more. So moving forward, I want to talk about a couple of things, and those are the main AC solutions from Altair is presented through the SRAM suite. And in this occasion, we're going to go through a lecture or viewing into how we can use SimSolid for these applications. Now, the reason why I mention this is because we use SRAM suite for design, while SimSolid is sometimes, or it's used for simulation processes. When we're talking about the design or the SRAM suite, we're talking about analysis, code check, and design that can be run through this software. Here in the top right side, I have a screen capture of a structure that was built in SRAM. And when we are moving to the main topic of this presentation, that is about the wind loads, we're talking about that those are being applied according to the building code. It also led us to know that those are automatically generated at floor locations according to the code needs. So SFrame has this option to integrate those wind loads according to the code, so we don't really need to input that data by each story, so we can, or each floor. We can just input some data and then that will be distributed into the structure. On the other side, when we're talking about SimSolid, we have a high detail simulation results that could be extract from this. Contrary of what's working with S-frame, that we input some data and that creates the equivalent of the wind loads. In the case of SimSolid, the data input goes through a wind profile, and we need to define a direction and a few other parameters that we're going to see later during this presentation. And most importantly, this is for analysis purposes only. We are not running any kind of code check or design process in SimSolid. This is only for analysis to verify that the results could be acceptable for our criteria. Now here in the bottom side, I have a render. This is not from SimSolid, but this is a structure that we'll see further in our presentation. Getting more into the main topic, I was mentioning about the wind loads in SimSolid, and those are defined with wind profiles and a few other parameters. Those profiles are divided basically into two main shapes, being the normal profile that goes with this straight line, and it's basically taking like a mass of air and pushing it in the direction. It's a regular mass of air. And for this, we are going to make use of the speed and the height above ground. Those are the data that we are going to use to define this normal profile. On the other hand, we have the logarithmic profile. And this logarithmic profile will make use of three main things that goes for the shear velocity, the von Karman constant, and the height above ground. We can also see here in this screen capture that we have the equation that is being used to define this wind profile, and we can clearly see that the shapes are not the same. We are seeing that at the base there is a very low, let's say, mass of air, and then it does increase when we are moving forward, going almost into infinite based on this, and this is the shape that the mass of air takes when you're pushing it into the structure. So based on this information, we can notice that the upper part will receive more load than the bottom parts. And we're going to see that later during this presentation when we go through the example. Now, we can start looking at one of the models. And for that, what I'm going to do is opening, in this case, Inspire. So here we can see the structure that we are going to look or review during the presentation. This is a square elevator shaft. We can see that it's composed by a soul of steel elements here, square elements that are defining the main frame. And then we have the glass panels that are for goes for 2 meters in one direction and 3.2 meters in the other direction. And then we have some connections here, some pieces that will connect the panels with the main frame. You can even render this part just to see about the materials that we applied to the structure. And then after a process that unfortunately it's a bit out of the scope of this presentation, we can migrate this part or export this part to SimSolid. And I have it right here. The reason that I showed the previous image was mostly because you will see we're not seeing the translucent elements, but those are defined as opposed to in terms of material. Here we can work into a bit of setup, but in this case, most of the setup has been done. So we can just go through the main topics, but it's a good idea to review what we have done so far. And for this, I'm going to the assembly part, and I'm going to review the applied materials. And here's when I can make sure that everything is defined as supposed to. First, going that the steel was assigned to the main frame, to the elements. The glass was defined for the panels. And we see some tiny gaps here that goes for the urethane. That goes for that material that will connect the panels. And the work of this of those little pieces is making sure that everything is connected as supposed to. Now I'm going to take a look into the constraints. In this case, for the loads and constraints is going to be run in structural linear analysis. I can click on edit and review my current constraints, which are being defined as unmovable. And we can see that we have eight constraints here. 4 of those goes for the columns right here, for the floor, the ground. And then we have another 4 constraints right here. And those are basically working as a connection for the main building. If I zoom out, we can consider that if this part is where the main building will be. And then we have here those pieces, those elements that are connecting the shaft with the rest of the structure. This is how we interpret those constraints. Then we have also our gravity load. You can just click on edit and review what's the value that was input. If we see here our coordinate system, we can see that the C duration goes for the gravitational loads, we can say. And this is defined here in the gravitational load with a negative value of 1. So with all of that being said, we are in shape to start defining a few things. And that goes for the wind load itself. So I'm going to open this part and it says wind load. I'm going to select this, and here I have the window that will help me to set up the information that I want to work with. First, it goes for the wind profile. And I can just click here and create profile. Since I don't have anything defined yet, I can see here that I have in the left side diagram of the current points. I don't have any point defined yet. And then I have the values of those points. It goes for the speed and the height above ground, as we can see here. I can just add different rows, input my values, but I'm not interested in doing that, not manually at least. I'm going to delete it. I can also import information from a .csv file, because that I have it, or I can make use of the wind profiles that are defined or that are possible to define here in SimSolid. So I'm going to click on Standard, and now I have the chance to refill this information. So at this moment, I have one of the wind profiles that I showed you before that goes for the uniform profile type, that goes for the speed and the height above ground. And it goes with this shape. And then we have the logarithmic profile. Before inputting anything or keep looking at this, I want to get back to my slides. And the reason because of this is that I want to take a moment to see a bit more about how the logarithmic profile works. This is mostly defined, or the equation that's been used is mostly for the 2D turbulent fluid flow. And we have a few things that we can define or add in what's the meaning of that. The first being the VZ, being for the local time average streamwise velocity. We have right here. We have the Z being the perpendicular distance from the wall. And then we have the wall shear velocity. That is being defined for this short equation. And for the equation, we have that tau 0 is boundary shear stress, while rho goes for fluid density. And lastly, we have the key that goes for the von-Karman constant. Now, this von-Karman constant is something that was defined through different experiments, and there is no like a precise consent into or about how's the true value of this constant. Different conditions gave different results about what the von-Karman constant should be, but in general, for practical purposes, it's been defined as 0.41, and that's the same that's been input in SimSolid from scratch. So now I can get back to my my model in SimSolid. We have a bit more. Hopefully, we have a bit more of understanding of what we're doing. And then we can start inputting a bit of data. Now, for the shear velocity, I'm going to go for a 0.45 meters per second. The von-Karman constant will remain as the same. And in this case, the height above ground goes for the total height of the structure that I'm reviewing. In this case, my structure goes for almost 10.8 meters height. So that's why this is inputting this value, just a little below that measurement. So that's why it's not in the close 800 millimeters. But for practical purposes, it works for us. And most of the times, though, that value of the height above ground will take the highest value or the highest height, we could say, of the current model that we are reviewing or trying to analyze in SimSolid. So with all of that being said, I can click on OK. And I can see now a wind profile that's been defined based on the logarithmic information that I input. And I have here all the information related to that. The speed and the height above ground, in case that I want to review a bit more of this. So I'm okay with all that information. Then I can start paying attention to other stuff here in my wind load window. Here I can move the coordinates of the ground point that we'll consider that it's been to place the window. For that, I can see that it's been defined, we can say, or the zero axis or the application point is being just in the corner, but maybe it's not too good for visualization, so I'm going to change it. I'm going to move it nearly 200 millimeters in both X and Y direction. We can see it moved, and in case there are some doubts about how this placement was assigned, we can see here at the coordinate systems. I can rotate my structure and see that the wind profile goes in this direction, going like upwards, like an uplift, and this is not what we are intending to. For the sake of this example, let's say that I want to apply this load, this wind load, this mass of air being pushed in this phase. I have it right here. And for that, I need to change a few things. First of all, being for the wind direction. You can see here that the wind direction has been defined as in the z-axis, being the uplift. And this is not that I want. I mentioned that I want it in this phase, and by looking at the global coordinate system, or the global coordinate system here, I can assign the correct value that will be a positive 1 in the y direction, but I'm still finding some issues. And the reason of this issue goes for the higher axis. I can adjust this part. We can see that it's in a -1 value, but what I'm going to do is change this part to just 1. And I can see now that the wind profile is being applied in the correct direction, or to the side direction. If I zoom out this view, I can see here a more clear shape that is more similar to what I defined here in the wind profile. See here, as we can see in this part. So I'm zooming in once more. And what the information is saying is that if we go to up review, let's say, I think it's from, yeah. So we're considering that there's a mass of air from this part that's being pushed from this direction, from below, we could say, to this part, to this side. So there's a whole regular shape that's been, or shape we can say, from to the sides is regular, but we know that the profile is different, right? But it's been, the air is being pushed regularly or uniformly from this side to this other side. And obviously, this phase, or those panels, are going to resist that. To make sure that everything is working as supposed to, we need to also to review that we have the enabled shielding as toggle on, because this is how we are telling SimSolid that this phase is the main phase that will receive or the first one that will receive the whole wind. With all of that being said, I can click on OK, and I can run my analysis. Just wait for it to finish. This shouldn't take too long. This is not a very complex structure, but in general, this kind of loading won't take that long to finish. And it's also a good chance to see how fast SimSolid can be when dealing with those sorts of things. So just in a moment, this should be done. We're in the last part of the analysis. And we are almost done here. And now we're really done. I can review the information, see that it takes a bit less than 40 seconds to finish. So it's a good time in general. And the one information that is important to us is placed right here in the post-processing tools, and mostly for the displacement. So I'm going to see the displacement magnitude, that is the whole summarized all the information, and I can see here a visual representation of this displacement. So you may ask, how is that visual really happening? What I can do is adjusting a bit of how the image is being rendered, maybe adjusting a bit of the shape, or maybe 8, and run my animation. In this case, my scale was a bit too high, so this is like penetrating into the frames here. But taking a look at the displacement magnitude here in the legend window, we can see here that the maximum displacement goes for 2.15 centimeters. If you remember correctly, the measurements of those panels are 2 meters per 3.20 meters. So I can also review on the maximum values, maybe just adjusting a bit of the shape, scale factor, just reducing it a bit. So it's not penetrating, but we are seeing that if we see this in a side view, how's the panel being deflected by the wind load that we just applied a moment ago. Just change here, and we can see also that the reference point is moving. And this goes for the general summary of the displacement here. I can also take a look for some particular axis. Look for displacement and maybe for the x direction. And we know that the x direction wasn't the place that the element or the dot was applied, but there are some values related to how this is being deformed. And the reason of that is that even if this face is receiving all or resisting all of that wind load, it's connected to the rest of the structure. So all the structure is being, in a certain way, being loaded one way or another. We can look at the y direction, that is maybe the most important for this particular application, and see how it's being deflected. But also, this is not limited to the displacements only. Maybe this could be the most useful information for some of the users that are applying this. But we can also take a look at the stresses, for example, the one stresses. It also shows a short animation or a subtle animation on the places that contain or condense the major stresses. For example, we can take a look at the major one, and then we take a closer inspection. We can see here subtle deformation or a subtle animation that's happening, while the rest is being absorbed by the elements right here, as we can see here. And we try to maybe rotate this part, and we can take a closer look, and we are seeing that this is the strain being, or the stress is already being expressed. These elements that have been connecting the main frames with the panels. Goes the same for the strains. Now it is correct for the strains, and see the animation, how things are working. We can see here that the animation goes accordingly from one point to another. So we have a continuity here. That means that our elements were correctly connected. And I can still review other information in case that I'm interested in. But for by far, we have just reviewed of this application in one single direction. But we know that the wind is not being pushed in one single direction, so we can integrate a bit of diagonal blow, we could say. For that, I'm going to stop my animation. Going for the wind load, right click and click on edit. Now, I don't want to change anything related to the loading itself, more about the wind direction. That's why I'm going to the wind direction tab. And in this case, what I'm going to do is going for, let's say, a combination of factors. At this moment, we know that for a single for a single value, it goes only for one direction, but I want to integrate a bit more of that. So let's say that I want this on maybe point 0.3 in the y direction, and then I'm adding a 0.7 in the x direction. And what will happen, as we can see, is that we basically rotate our wind loads or wind profile rather. And now, instead of just going from this point to this phase, now we consider that it's going something more similar to this direction, from this part to this part, and this will cause that both of those phases will receive and resist the load. So with all of that being said, I will click on OK, and I will run my analysis once more. Just wait for it to be solved. It wouldn't take that long as mentioned before. And now we're going to see a more realistic uh, simulation of a wind profile. We know that it's not common that it goes only for one direction, and especially since we can control this factor of the wind direction. So that's why we might want to take a look into different setups on how the wind will push to our shaft. We have finished our analysis. You can take a look into how long it takes. It was even less time, a bit more of 30 seconds. And I can take a look into the displacement manager and see how things automatically are changed. In our previous, let's say, try or loading, we saw that most of the displacement was just concentrated in this side. But with the change of the orientation of that wind profile, we now are receiving some displacements in this part. I once more can review the max values. They are not going higher than 2 centimeters, which could be pretty good. Obviously, it depends on the material properties and the kind of glass that you're using and some other factors, but in general, those are very low deformations. And I can also review the animation, and I just place it so I can see how this is being deflected, maybe from this part, and see how's the deflection being here. And obviously that will be the same for this face. Actually, we can see directly behind of this, but we can understand the idea of what's happening right here. And that goes for most of the rest of the post-processing tool that we saw. So for the stresses and see the stresses. And we can even see a bit more maybe the fine shapes here. Now we are not just limited to one side that's been presenting this deformation, but both of the sides, since both faces are resistant the winds. You can rotate and try to take a look here. I'm watching here stresses, and also in this part I can adjust this and see how this is resistant. So this is basically the way that it works. We can define a few, review other values here in any particular specific direction that we may want. Maybe this deformation just for the cell weight, or the displacement in one single direction based on the current profile. It's up to the user, to us, to see what information is useful for us. Now, before finishing, I want to see another example that, fortunately, we don't have enough time to go through all of this setup and see the results, but I have here some screen captures of that structure. Here I have a plate that has the Altair logo and the Altair words, or letters, rather. And this plate is, and the plate is at the top, and the plate was placed in a concrete wall. You can see right here. This was defined as a movable. The wind load was applied in the direction of the plate, and we can see here the displacement that's been happening due to that wind load. We can also see here in let's say sided view how's the deformation going and how's not been deformed on other parts. That goes or are making sense with this front view. We can see here some sections, some, let's say, straps that are not deforming, and that goes because that's where the connection of the plate to the wall is happening. And it goes basically by having the correct geometry, and we can run our analysis and start validating if that works for the win loss that we expect. Thank you for your time watching this presentation. I just want to remind you that this will be uploaded to our YouTube channel in case that you want to review any other topic. And you can also reach out in case you have any specific questions related to the topic. I was Alejandro Lopez. Thank you for your time and have a good one.